Hello everyone. Let's discuss about frequently asked questions from D and F block elements and how to write appropriate answer for all these questions. So let's start. First question. Write general electronic configuration of D block elements. So in answer we write n minus 1 D1 to 10 ns 1 to 2. Second question. What are D block elements? D block elements are those in which the last electron enters in d subshell and they have partially filled d orbital either in their elemental state or in a stable ionic state. So all these elements or ions which have partially filled d orbitals, they belong to D block element. Next question. What are transition elements? Transition elements are those which lies in between in S and P block elements. They show transition in behavior. S block elements are electropositive in character. They are metallic in nature, whereas the P block, they are electronegative and non-metallic. Next questions regarding zinc, cadmium, mercury, uh, they do not have partially filled d orbital. Still, they are the part of D block element. Why? Because they show the same kind of behavior as shown by the other D block elements. And the other point we write along with this, they are the end members of 3D, 4D, and 5D series. So the question is, in spite of having completely filled D configuration, zinc, cadmium, mercury, they belong to D block elements. Why they are considered as a D block elements? Because they show the same kind of behavior as shown by other D block elements, and along with this we write they are the end members of series. Next point, next question, name the elements which have low enthalpy of atomization. So zinc, cadmium, mercury, they have low enthalpy of atomization because they have a fully filled orbital. Because of the absence of unpaired electron, the metallic bonding is weak. That's why they have a weak crystal lattice, and this results in low enthalpy of atomization. And one more important thing, if we talk about the zinc, so its configuration is 3D10 4s2. All the electrons are paired up here. So in this case, interelectronic repulsions are maximum. So this result in weak metallic lattice, and that's why they are soft and have low melting point and boiling point. So any of the question which is concerned with zinc, cadmium, mercury, so we follow these points, like they show the same kind of behavior as shown by the other D block element. They are the end members of the series. They have fully filled d orbitals. So that result in a weak metallic bonding, weak crystal lattice, low enthalpy of atomization, because all the electrons are paired up. So maximum interelectronic repulsion. That's why they are soft metal and have low melting point and boiling point. Next question regarding the D block elements is, why do the D block element, they show variable oxidation state? So in our answer we write, in D block element they show the variable oxidation state because of the comparable energy of D and S orbital, and both these orbitals S and D, they participate in a bond formations. For example, if you talk about a manganese Mn, its configuration is 3D5 4s2. In Mn2 plus, it is 3D5. In Mn4 plus, it is 3D3. In Mn7 plus, it is 3D0. So all these configurations are possible because of the active participation of D as well as S orbital in the bond formation. One more question, that one is framed here. Name the elements which do not show variable oxidation state. That one is zinc and scandium. Scandium is the very first member of a 3D series. Its configuration is 3D1 4s2. It has only one electron in a d orbital. Whereas zinc, its configuration is 3D10 4s2. All the electrons are paired up here. Next is, They show catalytic behavior. So why do the D block elements, they act as a catalyst? Because they show variable oxidation state. They form an unstable reaction intermediate activated complex in a higher state, which is unstable, provide large surface area. For example, in a contact process for the formation of sulfuric acid, we use vanadium pentoxide. Next question. Why D block elements, they are paramagnetic in character. Paramagnetic means they have unpaired electrons. More the number of unpaired electrons, more the paramagnetism. Next is, like suppose we talk about the, we are having manganese. Its configuration is 3d5 4s2. So in case of manganese, number of unpaired electrons are 5. Mn, that one is 3d5. Whereas Mn2 plus, it doesn't have an electron in s orbital, so it simply has 3d5. If you talk about Mn4 plus, two more electrons are removed from d orbital. Now its configuration, it becomes 3d3. So in Mn2 plus we have 5 unpaired electrons, whereas in Mn4 plus we have 3 unpaired electrons. Next property is about a magnetic moment. Calculate the magnetic moment or spin only moment of a given compound or a given ion, particularly ion whatsoever is. So in that case, we use a formula. Magnetic moment is a square root of n into n plus 2, where n is the number of unpaired electrons. Suppose if we talk about calculate the magnetic moment of manganese in MnCl2, we are having a compound MnCl2 and you have to calculate magnetic moment for manganese here. So in MnCl2, manganese is divalent, Mn2 plus. So in Mn2 plus, it has 5 unpaired electron here. So n here is 5 in this case. So it becomes 5 into 5 plus 2. So 5 plus 2 is 7. 7 into 5, 35 Bohr magneton, B dot M. Next question. Why do D block elements are colored in nature? Because of the paramagnetic behavior, because they have partially filled d orbitals. So that's why DD transition takes place easily here. DD transition means electron-electron transition. Next question is, they have high enthalpy of atomization. High enthalpy of atomization means they have large number of unpaired electrons, which result in a strong metallic bonding. Strong crystal lattice formation is there. That's why energy required to break up that bond is quite high. So the enthalpy of atomization is higher in case of chromium, because the configuration of chromium is 3d5 4s1. It has 6 unpaired electrons. Next question. D block elements, they form alloys. Because they have comparable size, one metal can easily replace the other metal in its lattice to form a solid solution. They form interstitial compound that results because of a strong metallic bonding, and these gaps are known as an intrinsic site or a void. So because of the trapping of small elements, specifically second period elements we trap here, because of the trapping of smaller elements in interstitial sites, the resulting compounds are known as interstitial compounds. So in case of D block elements, they form interstitial compounds because they have voids, because they have strong metallic bonding, and that's why trapping of small elements takes place in interstitial sites. Next, if a question is about copper, its atomic number is 29 and its configuration is 3d10 4s1. Half-filled and fully filled configuration are more stable. That's why the transfer of electron takes place from s orbital to a d orbital in order to make it fully filled. Now Cu2 plus is 3d10, most commonly shown +1 oxidation state. That one is by copper, univalent copper. Then in Cu2 plus it is 3d9. Now the question that one is asked from this part, first question, Give an example of an element which commonly show +1 oxidation state. In that case, we give an example of copper here. Second question, that one is asked from this part. Why divalent copper Cu2 plus is more stable than Cu plus 1 in aqueous solution? Why so? Because divalent copper is smaller in size, that result in more hydration, so its hydration enthalpy will be higher. Copper 2 plus, its size, small size. Small size means more hydration, as a ion dipole interaction is more. Ion is a copper ion, Cu2 plus. Dipole is a water. So as because of more ion dipole interaction, its hydration is more. And because of higher hydration, more amount of energy is released. High hydration enthalpy, and hydration enthalpy is a negative enthalpy. Value is in negative. Why so? Because of attraction between ion and a dipole. So why trivalent copper is more stable in aqueous solution? Because its hydration enthalpy is more than that of the sum of the ionization and enthalpy of atomization. Next question frequently asked from this part, that one is, its E naught value is positive. Electrode potential is positive. Electrode potential is basically a sum of enthalpy of atomization, ionization, and hydration. Enthalpy of atomization and ionization, these are the positive values. Whereas the hydration enthalpy is negative. It means whatsoever the element is, if E naught is positive, it means atomization and ionization sum is more than that of the hydration. And if in a question E naught is negative, it means hydration enthalpy is more than that of a enthalpy of atomization and ionization. So E naught positive when E naught is positive, when hydration enthalpy, that one is more. And if it is positive, it means hydration that will be less. Next part, oxo anions. Now the question asked from this part is, okay, give an example of an ion or an element uh, in where the group number and the oxidation states are same. Or the question we frame from this part, okay, give an example of an oxo anion in which the elements show the highest oxidation state. So in case of manganese, as manganese belongs to a group 7, so we take an example of permanganate ion, because in a permanganate ion its oxidation state is 7 as well as its group number is also 7 here. Then let's talk about the chromium. Chromium, it belongs to group 6. So in this case, we take an example of chromate, CrO4 2 minus, or we can write a dichromate here. The next part, questions based on manganese. Manganese, that one is the center part of 3D series. Its atomic number is 25. So its electronic configuration is 3D5. 4s2. It has 5 unpaired electron, half filled and stable configuration. One most important point I just wish to share here, if there is any question from the D block elements, always try to give the answer on the basis of electronic configuration. Next question, on the basis of melting point. So high melting point because of strong metallic bonding, like in case, and when the metallic bonding is strong, stronger metallic bond means more number of unpaired electrons. So if I just take an example of iron and copper, iron, its atomic number is 26, so its electronic configuration is 3d6 4s2, whereas the copper, its atomic number is 29, so its electronic configuration is 3d10 4s1. So iron, it has 4 unpaired electron, whereas a copper, it has 1 unpaired electron. In case of iron, number of unpaired electrons are more, so that its crystal lattice, that one is stronger than that of copper. So that's why its melting point is quite high. Next part is covalent or acidic behavior or ionic or basic. All these questions we frame answer with the help of Fajan's rule. According to Fajan's rule, smaller size means higher oxidation state, more polarizing power, more covalent character. Smaller the size, more the polarizing power, more the covalent character. And in case of iron, if we have Mn2 plus like an Mn4 plus, Mn4, that means a higher oxidation state. It means the number of vacant orbitals here are more than that of the Mn2 plus. It means it can accommodate more and more electron. So that's why acidic. Covalent, acidic, ionic, basic. So if you just compare an example MnCl2 and MnCl4, MnCl4 is covalent and acidic because its oxidation state is higher and it has more number of vacant orbitals, whereas MnCl2 oxidation state is lower, so it is ionic and basic. Next question. That one is based on hard or soft metal. Hard metal means maximum number of unpaired electrons, strong metallic bonding, high enthalpy of atomization. So the best example here is chromium because its electronic configuration is 3d5 4s1. It has maximum number of unpaired electron in 3D series. And if you talk about the last member of the 3D series, that one is soft metal. Zinc, because its configuration is 3d10 4s2, it doesn't have any unpaired electron. Next, maximum number of compounds they form with fluorine and oxygen. Why? Because fluorine and oxygen both are the most electronegative element. Fluorine is the most, FON, fluorine is the most electronegative, then oxygen, followed by nitrogen. And the most important part here is oxygen has a unique ability to form multiple bonding. So what type of multiple bonds are formed here? Suppose we are having MnO4, like there is a double bond between manganese and oxygen. So d orbital of manganese form a multiple bond with p orbital of oxygen. So the type of multiple bonding here is p pi d pi. Then why do they form complex? D block element they form readily form complex because the partially filled d orbital, they have sufficient number of vacant orbitals in which they accommodate the electron pair. Ligand, that one is an electron donor species. So there exists a coordinate bond between the metal and a ligand. Vacant orbital of metal that form a bond with the filled orbital of ligand by donation of electron from ligand to metal side. Next part, next question frequently asked from this part is irregularities in ionization enthalpies that arises because irregularity in radii, extra stability of half-filled and fully filled orbital, and after the mid of the series, interelectronic repulsions, maximum scandium, titanium, vanadium, chromium, manganese. So till manganese, its configuration is 3d5. No pairing of electron is here. But manganese, after manganese, the pairing of electron takes place that result in increase of interelectronic repulsions. Then the questions based on cerium. Cerium, its electronic configuration is xenon 4f1, 5d1, 6s2. Ce3 plus, that one is 4f1, Ce4 plus, which is stable because it doesn't have an electron in the 4f orbital. So this one is widely used and as an oxidizing agent in volumetric analysis, that is in analytical chemistry. Few of the elements, metals, they do not replace, they are not able to replace hydrogen. Or a question is like, then they do not react with dilute acid. Why so? Metallic, so they have a protective oxide layer, and the most part, they lies below the hydrogen. That's why they are not able to displace hydrogen from the lattice. Oh, sorry, from the acid. Then what is lanthanide contraction, its consequences and its cause? Lanthanide contraction is basically a steady decrease in size with increase of atomic number. The cause of lanthanide contraction, that one is the poorest shielding effect of f orbital. And the consequences here are comparable atomic size. Sometimes they give a, why do zirconium and hafnium they have a comparable atomic size? Then you simply write because of lanthanide contraction. Difficulty in separation of them. same chemical properties, and the size of lanthanide decreases from lanthanum to lithium. So the covalent character of the hydroxide increases, and hence the basic character decreases. It means from La to Lu, covalent character increases. So that's why the basic character decreases here. Next question. That one is based on the cobalt. Cobalt is able to form a complex. CO2 plus is stable in aqueous solution but oxidized to CO3 plus because of its fully filled T2G configuration in the presence of a SFL. SFL is a strong filled ligand. Iron, cobalt. Our series is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Scandium is 3D1, then 3D2, 3D3, 3D4, 3D5 is manganese. Cobalt is 3D7 we have, and nickel is 3D8 and 3D9, which changes into 3D10 finally, and then the 3D10. The next question, mixed metal or a pyrophilic alloy. That one is a rare earth alloy consisting of 50% cerium, 25% lanthanum, and 50% niobium, and 10% other rare elements. And so this one is being pyrophilic in nature. That one is used in shells, lining, tracer bullets, etc. Then the next question, data, that one is given to you, ionization enthalpy is given, and they ask you which oxidation state is more stable for nickel and platinum. So if you just compare the data like IE1 plus IE2, you just add on these values, then for nickel that one is lesser, it means Ni2 is more stable. The one which is having lesser value of the sum of ionization enthalpy, that oxidation state is the most stable one. Like if we simply talk about the fourth oxidation state, so IE1, IE2, IE3, IE4, that will be a lesser for platinum. That's why platinum 4 is more stable than the nickel 4. Or they frame a question like K2PtCl6 exists. So in K2PtL6 platinum, that one show +4 oxidation state. But K2NiCl6 does not exist. Why does it exist? Because its sum of ionization enthalpy is quite high. So what we write in answer? Platinum, it shows +4 oxidation state because its sum of successive value of ionization enthalpy, that is lesser. Next question. E note, that one is a sum of atomization, ionization and hydration. If hydration enthalpy is more, hydration enthalpy is a negative value, then the E naught value will be negative. If hydration enthalpy is lesser, then the E naught value is positive for a given compound or a radical. Then 3D, 4D, 5D series. 4D and 5D series, that they have a larger size, strong metallic bonding, high enthalpy of atomization and high ionization enthalpy. Next part. Question based on lanthanide and actinide. So I am simply writing here in a tabular form the points of difference between the two. First point, configuration. For lanthanide, it is 4F1. They belongs to 4F series, whereas the actinide, they belongs to 5F series. So their configuration are 4F 1 to 14, 5D 0 to 1, 6S 2. Whereas for actinide, it is 5F 1 to 14, 6D 0 to 1, and 7S 2. Stable oxidation state shown by the lanthanide, that one is +3. Along with +3, they also show +2 and +4. And in case of actinides, they show a +3 and also show +4, +5, +6, and +7. Colored ions, lanthanides, they are colorless, whereas actinides, they are colored. Complex formation, lanthanide have lesser tendency to form complex, whereas actinides, they have more tendency to form complex. More tendency means they have more number of vacant orbitals. They easily accept electrons from the ligands. Then the next part, basic nature of oxide and hydroxide. Lanthanides are less basic, whereas actinides are more basic. Radioactive, not radioactive. Lanthanides except promethium, whereas all the actinides are radioactive. Magnetic properties that can be easily explained, whereas in case of actinides that is not easily explained because they are radioactive, they are unstable in behavior. Oxocation formation, lanthanides do not form oxocations, whereas actinides they form oxocations like UO2 2 plus, PuO2 2 plus. Shielding effect. 4f electrons have greater shielding effect, so therefore contraction in radii, that one is lesser here. In case of 5f electrons, they have poorest shielding effect, so the contraction in radii, that one is more here.